Good morning. Last class we have discussed Pinacol pinacolone rearrangement by taking a symmetrical 1,2 diol. And in this class, another example of Pinacol pinacolone rearrangement. And in this class, instead of a symmetrical 1,2 diol, we are taking unsymmetrical 1,2 diol. So look at here, C6H5, C6H5, OH, CH3, OH. Correct? That means C6H5, or you can write it as you can show it in the form of benzene ring also, no problem. Okay, you can show like this also. In the form of benzene ring. So here you can see that this is unsymmetrical 1,2 diol because this OH is attached to this carbon and the carbon is joined with the 3-methyl group. But in this case, the OH attached carbon is attached to phenyl groups. So this is an unsymmetrical 1,2 diol. In the case of unsymmetrical 1,2 diol, when it is treated with mineral acid, what will happen? It will undergo pinacolone rearrangement, and we get two products. And let us see what are the two products and which one is the major product. Okay, look at it here. First, okay, let us take, look at it here. Okay, now we are taking this OH group. And last class we have discussed what is the first step. The lone pair electron on the oxygen atom will abstract the H plus ion from the mineral acid, and we get what we get C6H5. I can write instead of ring, I can write it as C6H5. Okay, correct. Here it is OH. One more bond is forming. Therefore, oxygen is getting a positive charge, and here it is CH3 OH. Correct? And in the next step, what is happening? You can see that the H2O molecule, this is OH, H means H2O molecule is eliminated. H2O molecule is a good leaving group. It will be immediately eliminated. That means minus H2O, okay, minus H2O. So what will happen? We get C6H5, here also C6H5. And of course, when the bond is breaking from this carbon, because the bond is breaking from this carbon and H2 is eliminated, therefore this carbon is getting a positive charge, and here it is CH3 OH. Correct? CH3 OH. Okay, in the next step, what is happening in the next step? Last class we have discussed. This is a carbocation, and what is happening? The positive charge is on this carbon, and next carbon is OH attached carbon. From the OH attached carbon, what will happen? The alkyl group, this alkyl group will be migrated to the positively charged carbon. So we get, we can show like this. This CH3 group is migrating towards this positively charged carbon, and we get C6H5, here also C6H5, and here it will become CH3, and here you can see that C and C, here it is CH3, and of course here it is OH, here it is OH, correct? And of course it will get a positive charge. Since the bond is breaking from this carbon is getting a positive charge. And in the next step, what will happen? This pair of electron will be shifted to here. Okay, will be shifted to here. This pair of electron will be shifted to here, and we get a structure like this. Structure like this. Look at it here. C6H5. Here also C6H5, here it is CH3, and here you are getting C. Okay, I am sure this CH3 can be written like this, CH3, and what will happen, since the bond is shifting to here, it will become a double bond OH, and since the electrons are moving from oxygen, oxygen is getting a positive charge, and in the next step what will happen, this bond is this pair of electron will be moved to oxygen. That means H plus is removed, minus H plus, and we get C6H5, C6H5, here it is CH3, what will happen, here it is C double bond O CH3, we get a ketone. This is one possibility, we get a ketone. Okay, now you can see that the another possibility is attack of H plus on this OH group, or this lone pair of electron will abstract H plus, and we will get the second product. Okay, we will get the second product, and look at it here. Okay, I am going to the next product. Look at it here. Okay, I am keeping this part here itself because in the next step I need this formation of this carbocation is important. Okay, now in the second protonation means this one. Okay, so look at it here, H plus, this pair of electron, the lone pair electron present on this oxygen will abstract this H plus ion, and what do we get? Okay, look at it here, we are going, okay, let's go like this. Okay, we are getting C6H5, here also C6H5, and here it is OH. Okay, here it is OH because this lone pair is abstracting H plus, and here you are getting CH3, and here it is OH, and one more H with a positive charge, correct? That you know. And in the next step what will happen, in the next step, okay, what will happen, minus H2O, this bond breaks from this carbon, okay, minus H2O, and we get a carbocation like this, CH3, here is a CH3, of course here is a positive charge, and here it is C6H5, here also C6H5, here is OH. Okay, and in the next step what will happen, the OH attached carbon is this one, so from this carbon a phenyl group, okay, this C6H5, this C6H5 or this one of the phenyl group will be migrated to this positively charged carbon. So we are taking this phenyl group, this will be shifted to this positively charged carbon. The same time what will happen, this pair of electron will be moved to here. Okay, I am showing it in a single step because this bond is breaking from here and it is shifting to here. Simultaneously what will happen, the lone pair electron present on this oxygen will be moved between carbon and oxygen, and therefore here it will form a double bond. Okay, so we are getting C. Okay, here I can show this C6H5 like this, C6H5, and here it is O double bond OH, correct? And of course it will get a positive charge, and here it is CH3, here also CH3, and this phenyl group is attached to this carbon, so here it is C6H5. And in the last step, what is happening in the last step? Okay, this bond is breaking from hydrogen, and it is this pair of electron is moving to oxygen. That means minus H plus, we get C6H5C. So what will happen? The positive charge is removed, double bond O, and here it is CH3, here it is C6H5. This product we are getting. Okay, this product is we are getting. Now look at here. Which is the major product? When protonation of this OH group is happening, or the protonation of this OH group, due to the protonation of this OH group we get one product, and the protonation of this OH group, we are getting another product. So which is the major product, the first one or the second one? Okay, look at here. We can see that in this case, in the first case, this is our carbocation. This is our carbocation. Okay, this is our carbocation. So because minus H2O, here is a positive charge is created. Here positive charge is created. And in the second case, you can see that this is our carbocation. This is our carbocation. Okay, I am writing here carbocation, cation, and here this is our carbocation. Okay, carbocation. Okay, I am taking the carbocation in the first product and the carbocation in the second product. Okay, so keep it in mind. I am taking the carbocation in the first product and the carbocation in the second product, formed in the second case. Okay, now look at here. This is the carbocation. So C, here it is like this. Okay, I am showing with the bond. Okay, here also we are showing with the ring. Okay, here it is like this, and here it is a positive charge, and this is the first case. C, here it is CH3, here it is OH. This is the first carbocation, first one, and in the second case, the carbocation formed is what is that? C. Okay, here it is our phenyl group. Okay, here also phenyl group. Okay, okay, here it is what is that? OH, and here it is CH3, and here is the positive charge. This is the second case. Okay. Now we can see that this is if you take the second OH group, even this OH group is protonated, you are getting this carbocation. You are getting this carbocation. Okay. Now look at here. In the first case, when a carbocation is formed like this carbocation can be, this is the first one, can be stabilized by resonance. Stabilized by resonance. Okay, stabilized by resonance. What do you mean by stabilized by resonance? You can see that here is a positive charge. Now, okay, take this ring. Okay, this ring or this ring, any ring we can take. You can see that when a positive charge is created on this carbon, what will happen? This pi electron, this bond breaks from this carbon and it will be shifted to here. So what will happen? This bond breaks from this carbon and it will be shifted to here. So we get a structure like this. See, okay, here it is a ring as it is. Okay, here what will happen? Here, okay, look at it here. Okay, here it is like this. Here it will become a double bond because here a positive charge is here. So what will happen? This pi bond will be shifted to between these two carbons. So here it will become double bond. The positive charge is removed. Since the bond is breaking from this carbon is getting a positive charge. Okay, here it is a positive charge and here is the bond, here is the bond. Okay, and in the next step, okay, the rest is like this, CH3, OH. And you can see that in the next step, what will happen? This will be shifted to here. Okay, and what will happen? Since the bond is breaking from here, it will become a positive charge here, here it will become double bond. And what will happen? The next step, this bond breaks from this carbon and it will be shifted to, so here it will become a positive charge. And what will, in the next step, what will happen? This bond again will come back, and so what will happen? The carbon will get again positive charge. That time what will happen? The reverse, the double bond will shift, and that means the resonance will, etc. The resonance is continuing. That means you can see that by resonance, the positive charge on this carbocation, this carbon is reduced, or you can see that this carbocation is stabilized by resonance due to the presence of phenyl group, and we can see that more stable carbocation will produce the major product. So when you compare the stability of this carbocation and this carbocation, if come to this carbocation, this carbon is attached to methyl group and there is no possibility of resonance stabilization. So more stable carbocation is this one, because the carbocation, this carbon can be stabilized by resonance. There are two rings with the due to the presence of these two phenyl groups, this carbocation can be immediately stabilized. Therefore, the product formed from this carbocation will be the major product, and here you can see that there is no possibility of resonance stabilization for this carbocation. So the product formed from this carbocation is minor, and the product formed from this carbocation is the major product. Okay, so this is the case when we take unsymmetrical 1,2 diols. Clear? Okay, thank you.